To have a semantics, we need a language, and our language is going to be called while. So it's a while language. So if you Google that, you'll see this is actually a concept. So the while language. So language has 5 types of statements, and the most complicated one is the while loop, which is also the one that makes the language non-terminating. So you can potentially loop thanks to while. So at some point in my master's thesis, I pretended that while stood for a weakly hypothetical imperative language example. So you can form a backronym if you like. And then my supervisor said, you know that while doesn't stand for anything, it just stands for while. It's like, yeah, sure, of course. I invented the backronym, I know that. I know that very well, but that really messed with his brain. So this is while, a beautiful language. So the first statement is skip. Skip does nothing. It's a no up. So it's like an empty block, right? So you open a brace and you close a brace. That can be useful in a number of situations. For example, if you have an if then else and you want to omit the else, then you can put a skip in the else, for example. But it's always useful to have something that resembles 0. In mathematics, at least 0 with respect to addition. So that's the purpose of skip. Then we have an assignment. So you assign an expression A to a variable X. You have sequential composition. So you have one statement, semicolon, the other statement. So you're probably more familiar with languages where you put a semicolon at the end of every statement, including the last one, where the semicolon is a terminator. But historically, semicolons were separators. They were in the middle, and you didn't need them at the end. So I think that's how it was in Pascal and maybe Algol, I'm not sure. Anyway, so the while language is a bit old-fashioned in this respect. It sees a sequential composition as a binary operator, and the operator is called semicolon, and you put it in the middle. So it's rather a nice convention, actually, once you get used to it. Then you have a if then else, where you have a Boolean condition. Then you have 2 statements here. So I'm saying statement all the time, but some people would say command or even program. This is all the same to me. So a program is going to be one big compound statement or command. But typically I'm going to talk about statements. Okay, and then you have a while Boolean condition do s. So it's a while loop. It has the do keyword here to just cleanly separate the 2 arguments. Again, it's a bit old-fashioned. Yes, that's the grammar of what we're going to do. And the next thing we have is the type that goes with it. So this is how we would represent this. This is basically an abstract syntax tree in some sense. And this is here the same thing as an inductive predicate. And you'll see in exercises if maybe I've already asked you to do it or not, or the exam that might come. Often, well, sometimes at least I will ask you to take an informal textual description of something and transform it into a lean version of the same thing, because that's a very important activity that we do when we formalize, right? We start with the C standard and then we have to translate it to logic, right? So it's not always about proving lemmas that are cleanly stated and so on. So you have to come up with definitions as well. You have to state the lemmas and so on. And these are very important aspects of interactive theorem proving as well, which is why it pops up in the exercises and homeworks. So here what happened? Well, skip is just a statement. It takes no arguments. Assign takes 2 arguments. So variables we'll say are strings. But this part here is a bit special. So we're saying that, this is an expression. So we would have expected maybe AX, the type of arithmetic expressions. But we've done something else. So AX would be called a deep embedding, and we went for a so-called shallow embedding instead, which means that we use the language of Lean to represent expressions. So we're going to use basically lambda expressions to represent arithmetic and Boolean expressions. And that will become clear once I show an example. Okay, so it takes 2 arguments, returns a statement. Sequential composition takes 2 statements, returns a new statement. If then else takes a Boolean condition, 2 statements, and return a statement, and while is similar, but there's only one branch, right? And we're going to use the syntax semicolon, semicolon for sequential composition, because that's an operator that pops up all the time, and it's very useful to have it as an infix operator. For the other ones, we don't need any fancy syntax. I mean, this is just if then else, ITE in one word. Okay, and we need 2 semicolons because a single one is already used in the language for, you remember, you know, it's a tactic combinator that connects 2 tactics together. So let's write a program. I mean, just to see what this programming language feels like, especially once it's coded in Lean. So we're going to call it prog1 of type statement. And well, let's start with the easiest program that compiles. So we're going to say statement skip, and that works. But maybe we can, you know, have a composition of skip and skip. And then it would be nice to have an assign so that we see this this shallow embedding I mentioned in action. So assign to variable x. What do we want to assign? We want to assign. Well, we get the state as argument, then we can use the state to query other variables. So we can say take s of a plus s of b, and this is going to be our expression here. You see, so this is really a Lean expression. This is a shallow embedding. We just use Lean to express our expressions, which is quite convenient. We don't need to define our own language like AX with all the constructors and the evaluation function. Right? In some sense, what we do is, I mean, if you think of a type with constructors and an evaluation function, you create syntax, and then eval, the evaluation function just destroys it, right? And then it leaves you with some Lean expression, right? Well, here we cut the middleman or the middlewoman, and we just write the result without, you know, transforming it first into syntax and then unsyntaxes, like desyntaxify it or something like that, okay? And let's put all of that into a while loop. So we're going to have stmt while like this, and we need a condition, and it's the same game. So we're going to pick a state, and we're going to say s of y is greater than 0. And this is a while program here. Okay, so this is the discussion here about deep and shallow embedding. Here you have some examples of expressions. We already saw some, right? So x plus y plus 1 would be written like this. A is different from B, it's written like that. And now we're ready to see the operational semantics. Actually, we're going to have 2 semantics, right? We're going to have a so-called big step semantics and a small step semantics. And we'll start with the big step.